So welcome to tutorial 9. For question 1, N-butane is converted to isobutane in a continuous isomerization reactor that operates isothermally at 149 degrees Celsius. The feed to the reactor contains 93 mole percent of N-butane and 5% of isobutane and 2% of hydrochloric acid at 149 degrees Celsius, and a 40% conversion of N-butane is achieved. So you have 4 parts here. So for part A, taking a basis of 1 mole of feed gas, calculate the moles of each component of the feed and product mixtures and the extent of reaction. B. Calculate the standard heat of isomerization reaction in kilojoules per mole. Now then take the feed and product species at 25 degrees Celsius as references, prepare an inlet-outlet enthalpy table, and calculate and fill in the component amounts in mole and specific enthalpies in kilojoule per mole. Okay, so you want to look for the N and the H in both the inlets and outlets for each species. Now C. Calculate the required rate of heat transfer to or from the reactor state which it is. Then determine the required heat transfer rate for a reactor feed of 325 moles per hour. Oops, sorry for the mistake in the typo there. Now D. Use your calculated results to determine the heat of isomerization reaction at 149 degrees Celsius, which is delta specific heat of reaction at 149 degrees Celsius in kilojoules per mole. So let's look at question A first. So we take a basis of 1 mole here as the feed, and we calculate the number of moles of each of the component of the feed and the product mixture. Then we calculate for the extent of reaction. So this is pretty straightforward. So this is your equation, your reaction. Okay, so basically your NC4 is converted to IC4. Okay, it's just a different form of butane. Now, given the composition of the feed, we can easily calculate for the number of moles of C4, IC4, and HCl in the feed stream. For the product, we are going to calculate as so. So we were told that it is only 40% of conversion of N-butane is achieved in the feed. Therefore, N1, which is C4, is your remaining C4. So it is 0.93, which is N1 here at the inlet, multiplied by 1 minus 0.4. So this means that 60% of C4 is being remain in the product stream, and this leaves us with 0.558 moles of NC4H10. So for N2, which is IC4, so we take 0.93. Why? Because NC4 is converted to IC4 based on the 40% conversion. So 0.93 times 0.4, which is your 40% conversion, plus the original I4 in the feed stream. So the total of the feed stream and the converted C4 gives you N2, which is 0.422 moles. Now for N3, you have your HCl in, which is equal to HCl in, which is 0.02, because there is no reaction taking place. So to calculate for the extent of reaction, we will use NC4H10. So the extent of reaction is N out minus N in over the stoichiometric ratio, which is, from what we calculated here, over -1. Okay, this is -1 which leaves us with 0.372. Part B. Calculate the standard heat of isomerization reaction, then taking the feed and product species at 25 degrees Celsius as references, prepare an inlet-outlet enthalpy table as so, and calculate and fill in the component amounts and specific enthalpies. So we will use Hess law and table 1 to obtain the heat of reaction or isomerization. So this is one of the equation for the formation of IC4, and this is for NC4. Okay, so the heat of formation of IC4 that we can obtain from table B.1 is negative 134.5 kilojoules per mole. Now for NC4, or just C4 as we call it here, since we flip this over, okay, this gives us a negative value. So negative of the heat of formation of C4 is 124.7 kilojoules per mole. So why are we doing this is that we combine these two equations together to get the net reaction equation, or the isomerization equation for NC4 to IC4. So we cancel here, 4C cancel with 4C, 5H2 cancel with 5H2, and that leaves us with this net equation. So in order to get this, you plus this, right? So the heat of isomerization reaction is this value plus this value. That leaves us with negative 9.8 kilojoules per mole. So we draw the table and we input all the values that we have found in part A for the number of moles in the inlet stream and the outlet stream for each component. Then we determine the enthalpy for each species. So for H1 over here at the inlet, we integrate from 149 to 25 degrees Celsius, and we look for the CP value in the table for C4H10. Okay, so we integrate this equation, integrate CP, we get this equation. Okay, substitute your A values in and the temperature in, which is from 149 to 25. Okay, for this one is B over 2 multiplied by T squared plus C over 3 multiplied by T cubed plus D over 4 multiplied by T to the power of 4. So please take note, this one is not, you don't put 149 minus 25 and then 2 to the power of 4. That's wrong. So why we wrote it like this is because after simplification we get it to be like this. This is, so basically you substitute 149 into T, so it's 149 to the power of 4. And then you have your minus, then you put everything that has a minus the 25 in this equation, and we rearrange it and it simplifies into this form. So please do not put your 4 out here or your power out here. It is in its individual temperature. So we found that H1 is equal to 14.29 kilojoules per mole. So we do the same for H2 and H3, which is for IC4 and HCl. So for H2, IC4, same thing. We look for the A, B, C, and D values from table and substitute them in, and we integrate from 149 to 25 degrees Celsius. We get 14.14 kilojoules per mole. We do the same thing for H3 and we get 3.61 kilojoules per mole. So since the inlet and outlet are at the same temperature, since it was stated in the question that it is an isothermal system, therefore H1 is equals to H4, H2 is equals to H5, and H3 is equals to H6. Okay, the enthalpy at the inlet and the enthalpy at the outlet is the same because it is an isothermal system. So C, calculate the required rate of heat transfer to or from the reactor, the state which it is, then determine the required heat transfer rate in kilowatts for a reactor feed of 325 moles per hour. So we assume that it is a steady state with negligible Kz compared to the change, and there is no change of elevation, okay, and no shaft work being done. So this simplifies our energy balance equation into Q equals to delta H. Okay, so basically to calculate for our heat transfer Q, we need to find delta H. So the first option is using the heat of reaction method. So this is your formula for the heat of reaction method. Okay, we have already determined this and this and this for each species in part B, and we have determined the N in the outlet and N in the inlet from part A. Basically, we substitute everything in. Okay, and we get Q is equal to negative 3.7 kilojoules. Okay, since it is negative, it means that heat is removed from the reactor. So another method we can use is by using the heat of formation method. So when do you know that if you're using heat of formation or if you're using heat of reaction? So the heat of formation method is used when you have multiple reactions happening together. In this case, there's only one reaction, which is the isomerization of NC4. So we can opt for the heat of reaction method. You can also use that the heat of reaction method if you have multiple reactions, but it will be more confusing. Yeah, so to be on the safe side, you can use the heat of formation method. So to do so, this is your heat of formation formula, which is the formation plus the latent heat. So let's do NC4, which is H1 here. So HF, the heat of formation of C4, can be found in table B.1. And same thing again, we integrate its Cp for C4 from 149 to 25 degrees Celsius. And we will get this value. Okay, do the same for IC4 and HCl. Now for IC4, which is H2, okay, same thing. But notice that HCl, you do not have heat of formation. That is because this is a non-reactive compound in this system. It stays as an inert. Alright, so if this the compound is an inert, meaning to say it does not react with any of the components inside, then we will omit the heat of formation. Even if you go to the table, you will find the heat of formation, you will have a value there, but in this case, since there's no reaction going on by this HCl, we do not put it in here. Okay, clear? So delta H, okay, again, put everything in. So you have your Ni, your N1 multiplied by H1, N2 multiplied by H2, N3 multiplied by H3, and N1, okay, so on and so forth, the inlet and outlet. So that gives us delta H of negative 3.7. So the values from the second method is the same for the first method. So the question asks us that to find the delta H for 325 moles per hour in the feed. So we will convert this, okay, multiply it with 325 moles in feet per hour, and this leaves us with this value. Convert it into kilowatts with this conversion factor, we get 0.334 kilowatts. Now D. Use your calculated results to determine the heat of isomerization reaction at 149 degrees Celsius in kilojoules per mole. So the heat of isomerization at 100 and 409 degrees Celsius, okay, does not account for the latent heat from the inert HCl. Okay, same thing. So we draw the reaction pathway first. So over here we will need to determine HA, and over here we'll need to determine HB. HR was determined, okay, from part HR was determined previously in part B over here, okay. So HA is the latent heat from 25 to 149 degrees Celsius, while HB is this. So we have already determined this from part B. Okay, in this case it is a negative value, so we put a negative here, and H2 is a positive value, HR. So we sum all these values together, HA plus HR plus HB, and this gives us the heat of isomerization reaction at 149 degrees Celsius to be negative 9.95 kilojoules per mole.